This is part 2 of our best fit line work, where we will find the equation of the least squares best fit line passing through our 5 data points. When we left off on part 1, we had just found the center of gravity by averaging the x's and averaging the y's. That one point is the point through which every line of best fit will pass. Now if we take that point and we translate it to the origin, and we translate every other point using that same transformation, a slide to the left of 4 and a slide down of 6. So remember this transformation because we're going to be using the inverse at the end. That if you translate all the points so that the new center of gravity is at the origin, we can concentrate on this new set of data without having to worry about the y-intercept. Since the best fit line must pass through the origin, we know that the y-intercept must be 0 for that best fit line. We can concentrate on finding the slope of the best fit line here. Whatever the slope of the best fit line is for this set of data points will also be the same as the slope of the best fit for the original set of data points, since it was just a translation that moved these points here down to the origin. So we begin, just like we did with regular program fit, is what FITS does is it asks you for different slopes. If we pick a slope of 1, and we calculate the sum of the squares of the vertical distances by choosing the slope of 1, the y equals x line, find the vertical distance there is 1, 0, 0, 0, 1, square those numbers, 1 squared plus 0 squared plus 0 squared plus 0 squared plus 1 squared is 2. So that when the slope is 1, the sum of the squares of the vertical distances is 2. We just pick more slopes, so if this slope was 2, here's the line y equals 2x, find vertical distance, and find the sum of the squares of those vertical distances, which turns out to be 4. If I chose 3 as the slope, then this slope, or this vertical distance squared, this vertical distance squared, vertical distance squared, vertical distance squared, adds up to 26. Now, if we have a line that is off our graph, we simply have to calculate what the y-intercept on the line would be. So when the x-coordinate is -2, the y-intercept, or the line value would be, the y value on the line would be -8. The distance from -8 to 3 is 5, and 5 squared is 25. And then we would add 3 squared, 5 squared, and get 68 for our total. So what program FITS does for us is it does this automatically, takes the slopes that we feed it, it calculates the sum of the squares of the vertical distances by using the lists, and then it puts these numbers into list 4 and these numbers into list 5 for us. Remember that once we have that data, the slope versus sum of the squares of the vertical distances data will always form a perfect parabola, the y equals ax squared plus bx plus c, that should be a plus, type of parabola, where we can solve for the equation of the parabola by plugging 1 in for the x here and here, plugging 2 in for the y. That's this equation, plugging 2 in for the x here and here, plugging 4 in for the y, plugging 3 in for the x here and here, plugging 26 in for the y. And we get a system of equations which we can solve for a and b and c. This is what the system looks like after you expand it out. And our calculator QUADFIT can solve this, or you could solve this by hand, by elimination, and you would end up with the value of a is 10, b is -28, c is 20. So that means that the equation of the parabola y equals -10x squared plus -28 plus 20 would fit this data perfectly, no matter which slope we chose, which sum of the squares vertical distances resulted, they would all line up on this same parabola. Now there's one point that is the lowest point on this, which is the vertex, and that lowest point has the smallest sum of the squares of the vertical distances. So every point on this line represents a different slope, sum of the square of the vertical distances ordered pair, and the lowest sum of the squares of the vertical distances looks like it's going to be about here. So since I don't want to just estimate that, I want to calculate the vertex point by using the opposite of b divided by 2a, which in this case simplifies to 7/5. So when the x-coordinate is 7/5, that represents the slope that minimizes the sum of the squares of the vertical distances. So now I know that since 7/5 is the x-coordinate of the vertex, that point represents the smallest sum of the squares of the vertical distances. That point is the slope that I'm looking for that's going to minimize the sum of the squares of the vertical distances. So since the y-intercept is 0 in my set of data points I'm working with, that the 7/5 is the slope of the line of best fit, not just of this set of data points, but also of my original set of data points. So then I find the equation of the line passing through the origin is just y equals 7/5 x, And what I want to do is I want to take that to y equals 7/5 x, which is this line here, and translate it back so that it represents the original set of data points, which means it must pass through the center of gravity of the original data set. So the transformation method we can use is to take the y equals 7/5 x, put it through the inverse of the transformation that moved all these points to the origin in the first place. So taking the origin and moving it back would be 4 to the right and 6 up. Remember, the original transformation was 4 to the left and 6 down, so this is the inverse of that transformation. When I put this equation through this transformation, the x gets replaced with an x minus 4, the y gets replaced with a y minus 6 when I add 6 to the other side. This is the equation of the best fit line for my original set of data points. So if I put that line in here, that is the best fit line. That line with that particular slope and that particular y-intercept minimizes the sum of the squares of the vertical distances to the points. So this is my best fit line.